Hello students. So this is the second part of problem solvation topic that we were discussing from the first unit of artificial intelligence. In the previous session, we were discussing something related to this Romania map, and we have discussed a small function also, a simple problem solving agent. Simple problem solving agent which takes a percept, returns an action. Percept is the input and seq is a sequence that it initially would be empty, and the agent has to formulate that sequence, identify the sequence of actions which will lead to the goal state. So state is some description of the current world state, and then we have a goal. Obviously an agent has to reach a goal, so goal should be formed. Formulation of goal is required. So this sequence of steps happens in the function. A state is updated with the percent current state, and initially the sequence is empty. Let's now once again try to understand here. Once the sequence is identified, initially I don't know what steps I need to take, so sequence would be empty. But once the sequence is identified, like S1 to S2, S2 to S3, S3 to G, let us say goal state. Now A1 action takes me from S1 to S2, A2 actions takes me from S2 to S3, A3 action takes me from S3 to goal state G state. So this A1, A2, A3 and the states is that sequence is ready with me now. First of all, I will do one action in the execution phase: goal formulation, search and execution state. So in the execution state, once A1 is done, my sequence of steps now gets updated to A2 and A3. Next time I have a sequence to do. My sequence is not yet completed, so there this if condition does not get executed, and directly it goes for the action first of the sequence. This time it comes A2 and it returns. Likewise, all the actions are performed. Now we need to understand further this. Note that when it is executing the sequence, it ignores its percepts. So once it has identified the actions, it does the actions in a sequential fashion, and while execution, it ignores the percepts. Assume that you are driving a vehicle and the road is in front of you. When you are accelerating, you assume that the environment is static, the road is not moving, and the road is empty. So that movement, your percepts are not considered. It assumes that the solution it has found will always work. Now, the agent design in above assumes that the environment is static, as just now I have explained you, because formulating and solving the problem is done without paying attention to any changes that might be occurring in the environment. You can consider this as a simplified agent, not very complex agent, because the environment it is taking as static. So to understand how it can work, we are taking this sort of example. The agent design also assumes that the initial state is known. So from a known state, I am moving. Knowing it is easiest if the environment is observable. So that means we are considering a situation where the environment is completely observable. So the idea of enumerating alternative courses of action assumes that the environment can be viewed as a discrete. So here we are considering the simple formed environment. Finally and most importantly, the agent design assumes that the environment is deterministic. It knows what happens if some action is taken, how the environment is going to change. Deterministic environment we have considered. Now, well-defined problems and solutions. As the English saying goes, if a problem is well-defined, it is half solved. So how we can have a well-defined problem and solution? What it consists of? The well-defined problems and solutions will have one initial state that the agent starts in. Somewhere the problem should start from some point. So that is your initial state. Now, a description of possible actions available to the agent. So this is valid actions that the agent can perform. You should have a description of those things. Then we can have the most common formulation uses a successor function. What is the successor function? If let us say I have a state S1 and valid actions I can perform from this state is A1, A2, A3. Now what happens if I perform A1? I will go to S2 state. If I perform A2, I will go to S3 state. If I perform A4, I will go to S4 state, let us say. Now S2, S3, S4 are the successor states from state S1 on doing valid actions of A1, A2, A3 or A4, whatever we consider. So this is the set of states that are given by my successor function. So given a particular state x, successor function of x returns a set of action and successor like A2, S2, A3, S3, A4, S4, something like that, ordered pairs, where each action is one of the legal actions in state x and each successor is a state that can be reached from x by applying that particular action. So for example, from the state in array, like for example, we have seen this, this particular map. From the state of array, if you go to Sibiu, then you will be in Sibiu. From the state of Sibiu, if you go to Figueres, then you will be in Figueres. So go Sibiu in Sibiu, go Figueres in Figueres, go Bucharest in Bucharest. This becomes the successive things. For the array, Zerid, Sibiu, Timisoara are three successive states. Go to Jeren, you will be in Jeren. Go to Sibiu, you will be in Sibiu. Go to Timisoara, you will be in Timisoara. So let us try to understand this. Yeah. So this is how we can say in array, the successor functions for the Romania problem would return go Sibiu in Sibiu, go Timisoara in Timisoara, go Zeren in Zeren. Sorry, there is a spelling mistake here. Together, the initial state and successor function implicitly define the state space. So what is happening? You are considering all the states that can be reached from this particular state. That means that becomes the combination of all states. We call it as state space of the problem. The set of all states reachable from the initial state, that is called state space. This is very important to remember. And then I have a path to travel from S1 to S2 and then successor S3 for example, then successor S4, then goal state G. So S1 to S2 to S3 to S4 to G. This becomes my complete path. A path in the state space is a sequence of states connected by a sequence of actions. Now, if I am traveling, for example, consider you are traveling from your home to college. Now, in the path of travel, you should check yourself whether you have reached the college or not. So this is very important. If you are unable to test whether you have reached the goal or not, the action will never end. So there is a possibility of it goes into an infinite loop. So that is very important to have a goal test. Now if you understand very specifically, a such problem need to be performed again and again to find the solution. Actions need to be repeatedly done. That means it can be a recursive function. For a recursive function to end, one of the conditions is there should be some if condition where the recursion ends. So when I can end, if the current state is my goal state, then I can end further path traversal. So goal test becomes very important. The goal test which determines whether a given state is a goal state or not. Sometimes the goal is specified by an abstract property rather than an explicitly enumerated set of states. For example, if I say you have covered or you have crossed 40% of marks, then you are passed in the exam. So that may be your goal of passing the exam, reaching 40% of marks. So I can specifically mention in an enumerated set of states, if this is the state, then you are passed. Now what happens with chess example? Chess is also a game. I have got a goal state, but in case of chess, it is an abstract property. I simply say checkmate. A checkmate may be in many types. The point is cornering the cornering the king of the opponent without making it to move, without any possibility of moving it further. So that situation is an abstract property. So sometimes goal can be specified in both ways. A pathcast function. Now what is pathcast function? From start state, you are reaching a goal state, you are traversing different states. The cost incurred in traversing multiple states combinedly, you get a pathcast. A pathcast function that assigns a numeric cost to each path. Maybe, for example, you want to reach from Hyderabad to Vijayawada. So the cost incurred from reaching Hyderabad to Nalgonda, from Nalgonda to Khammam, from Khammam to Vijayawada. Combinedly, you consider it as a path cost. Now each individual part, whatever we consider here from Hyderabad to Nalgonda, that becomes a step of the path. So step cost, combination of step cost will give you path cost. A path cost function that assigns a numeric cost to each path. The problem solving agent chooses a cost function that reflects its own performance measure. So how performance need to be improvised based on whether less number of kilometers travel or less amount of time taken, or depends on the performance measure you are considering. The cost for mode of transportation, based on that it may be choosing one cost function. Now the step cost of taking action A to go from state X to state Y can be denoted like this, as shown in the slide. So what is optimal solution? I may be having multiple paths. Each path may have a specific path cost. Now, in case of greedy algorithms, the such algorithm will pick up the smallest path cost. So whichever is maximizing your performance measure, that becomes the optimal solution. A solution to a problem is a path from initial state to a goal state, but the solution quality is measured by the path cost function. An optimal solution has the lowest path cost among all solutions. The cost may be anything, price or maybe kilometers or maybe time, that depends what performance measure are we considering. Abstraction is where the state of the world includes many things, like when you are traveling, you listen to the radio, you speak to people, you look at the different locations, but all these things are not required. So you will only include important information, excluding certain information, that is abstraction. All these considerations are left out, which are irrelevant. So the process of removing detail from a representation is called abstraction. Now the first example of toy problems, if you can understand these problems, it becomes quite easy for you to understand the real life problems. These toy problems are like benchmarks for solving such mechanisms. Now first example what we can take is a vacuum cleaner. A vacuum cleaner which is there in two tiles A and tile B, may be moving from one tile to tile A. If the tile A is dirty, it will suck it. If the tile A is not dirty, then it may move to left or right. So initial state, any state can be designed as an initial state. The agent is in 1, 2 locations, the states, each of which might or might not contain dirt. Thus there are 2 into 20, 2 to the power of 2, this is actually 8 possible world states. So we have a successor function which generates the legal states that results from trying the 3 locations, 3 actions, left, right and suck. And the goal state would be clean. We can give path cost as step 1 cost, each step cost 1. So they have discrete locations. We can have further also, larger and one with n locations has got 2 to the power of n states. 8 puzzle. This is one very interesting thing what we have played in the childhood. For standard formulation I can give, a state description specifies the location of each of the 8 tiles and the blank in one of the 9 squares. Any state can be designed as an initial state, because like I randomly put all those things. Now you should not say I will pick up one tile and put it in the proper location. That is not possible. We need to move the slides and make it. Initially it can be in any slide position, initial state. Out of the possible states. Successor function is like legal states that result from the trying 4 actions of moving left, moving right, moving up or moving down. Goal test can be again anyone. I may be having 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or I may be having 9, 8, 7, 6, 5, 4, 3, 2, 1, something like this. Other goal formations are also possible. Each step movement I will take it as 1 cost, step cost as 1. So basically this 8 puzzle belongs to the family of sliding block puzzles, which are often used as a test problems for new search algorithms in AI. Now this general class is known as NP complete problem. If you look at 8 puzzle, simply it has got 9 factorial by 2, which is equal to 1,81,440 reachable states, and is easily solved. But when we increase its when we consider 15 puzzle and a 4 by 4 board, now I have got numbers from 1 to 15, has got around 1.3 trillion states.